Yeah, you want to use a pointer, but you have to click here.
Oh, okay, I have to click that. Thank you. Thank you for giving me this talk slot here. And my name is Takeru Suzuki from the University of Tokyo. Actually, this work is mainly done by Mr. Matsuoka as his undergraduate research. And he graduated from our undergraduate course this spring, this year. And he submitted the paper 1 week before his graduation. But unfortunately, fortunately, this paper will be published very soon. But unfortunately, he's in now nuclear fusion research field. So on behalf of him, I'm giving this lecture today. So on your right, I'm showing a schematic picture for the multi-layer structure on the sun. And these structures probably similar to stars or clusters with surface convective layer. So from the bottom layer is showing photosphere and chromosphere, transition region, and corona. And here I like to stress that the lower atmospheres are partially or weakly ionized. Then what happens? Dissipation or diffusion of magnetic field should occur in partially ionized plasma by ohmic diffusion via electron-neutral collisions in denser circumstances, or ambipolar diffusion. This is because of the drift between magnetic field plus choice components and the neutral components. So on the left top panel is showing ionization degree as a function of the distance from the photosphere. And this is normalized by the, in this case, solar radius. So as you can see, exceeds ionization degree. This is one fully ionized condition. In the chromospheric region, ionization degree is very small. It's an order of 10 to minus 4 or 10 to minus 5. Then, as a result, I'm showing magnetic Reynolds number. This is the ratio of the inertial term normalized by the dissipative term by magnetic diffusion. If this value is smaller than 100, no-ideal MHD effect is not non-negligible. Is non-negligible. Sorry, non-negligible. Then in the chromospheric region, here, this value is quite small. It's an order of 10. That means that the magnetic diffusion dissipation should be very important in the thermophysical dynamics in the chromosphere. So, of course, there are other potentially important processes like diffusion or kinetic processes, but in today's talk, I would like to ignore these effects. So previously, there are multiple or many works done by multiple groups. This is the result of the defrost simulation. In this case, one-fluid MHD. And the effect of non-ideal MHD is included by ambipolar diffusion mainly. And there are many panels. And the left case is for weak magnetic field, and the right is for strong magnetic field. So I like to only explain the top panels and the fourth panel. Top panel shows the magnetic diffusivity by ambipolar diffusion. So in the chromospheric region, magnetic ambipolar diffusion seems very important. In this fourth panel, they are showing neutral density. So in the chromosphere, or neutral density over total density. So in the chromosphere, the neutral is the dominant component. In recent years, two-fluid 2.5 DMHD simulation done by Muraski et al. And the top panel shows the velocity, drift velocity between neutral and charged particle. So here is the chromosphere. So in the chromosphere, we can see large drift velocity between these two components, which means that bipolar diffusion is very important in the chromosphere. So the purpose of this work is to study the effect of magnetic diffusion in the chromosphere on upper layers. Of course, in the corona and winds, the effect of no-IDMHD is not important because the gas is almost fully ionized. But if weak ionization in the chromosphere may affect on the thermodynamics in the upper layers. So in order to cover a very large region up to interplanetary space, we only use simplified treatment with one-third MHD with resistivity and ambipolar diffusion. And we consider the energy transfer in open magnetic flux tube, including with these no-IDMHD effects. So this is the movie showing simulation. The vertical axis is the distance from the photosphere. From left to right, I'm showing temperature, density, and the velocity for 4 cases. And in these 4 cases, IMHD, so without magnetic diffusion, and the case with only resistivity, and the case with only ambipolar diffusion, and the case with both diffusions. So weather colors the results with ambipolar diffusion. So the temperature in the corona seems to be lower for cases with ambipolar diffusion. And as a result of that, density is smaller. The velocity structure is very similar because this is mainly determined by the escape velocity from the system, from the star. So this table summarizes these 4 cases. So please have a look at the rightmost column. This column shows the muscle rate, although in this case, wind strength. So the cases with IMHD or cases with resistivity, the m dot is an order of the observed value for the sun. But if you include ambipolar diffusion, the muscle rate reduced by a factor of 4 or factor of 6 or 7. Okay. This is mainly because the pointing flux that can reach the corner is greatly reduced because of the dissipation of magnetic energy in the chromosphere. And as a byproduct of that dissipation, the chromospheric heating is enhanced in the cases with ambipolar diffusion. Okay. But maybe I should skip this. Almost time. Yeah, okay. So the previous study showed that by including ambipolar diffusion, the corona heating and the wind acceleration are greatly reduced. But the wind strength is recovered by a small change of a small increase of the pointing flux injection from the photosphere, only by a change of 20% phase perturbation. So this is because of the nonlinear aspect of the wind acceleration, but I'd like to skip this part in order to keep our time. Okay, so this is summary slide. So ambipolar diffusion is important, particularly in the dissipation of phonic pointing flux or phonic waves in the mid and upper chromosphere. And it enhances heating in the chromosphere, but reduces the heating in the corona and weaken the wind. So this will be more important in cooler cells because the temperature in the photosphere and the chromosphere is probably lower for cooler cells. So the effect of magnetic diffusion by no-IMHD effect, no-IMHD processes must be very important in cool cells. Thank you very much. I'm done.
Hello, I'm Julian Alvarado from the line.
Uh,
Great talk, thank you very much. I have a question about that last point.
okay.
That you said that it's going to be more important for cooler stars.
Yeah.
Because they're everything down.
Yeah.
But those stars also have much stronger magnetic.
Okay.
So could there be a compensation?
Yeah. Right. But ambiguous diffusivity is proportional to B squared. Therefore, stronger magnetic field will accelerate magnetic diffusion by ambiguous diffusion. So, yeah, it's